Hello, my name is Amisha Kapoor, and this is my Lab 2 video report. So I'll say the general purpose of this lab is to allow students to not only learn how the magnetic field is impacted by distance, but also how to accurately calculate the magnetic field of an object by accounting for Earth's magnetic field. Initially, I in specific was able to learn how to interpret collected data by looking at the graphs within the Excel spreadsheets for this lab. The general results were that the magnitude of B net that I calculated within the experiment in Excel was different than that which I modeled in GlowScript, being different by about 5.47 times 10 to the negative 5. And additionally, I found the general observation that the X value of the measured magnetic field increases as the observation location moves closer to the magnet, meaning that the distance decreases. As for general principles, I used the PHYS law, which essentially discusses how to find the magnetic field within a very small piece of a current holding wire, and this was the basis for the dipole formula that I later use, which on that note is important to note that I modeled the bar magnet as a dipole. And I use the idea that the strength of the magnetic field is dependent on distance, which becomes relevant later on when searching for the n value within the experiment. The experiment in particular required that we find the magnetometer within our phone, which is our system, and we do this by moving it around relative to our source, which is the bar magnet. After we do that, we essentially move the magnetometer on the same horizontal axis as the bar magnet, and by changing this distance in the x and seeing how it impacts our Bx value, which is our magnetic field's x component, we are effectively able to see how distance relates to the magnetic field, which is how we came up with the observation that the less the distance, the stronger the magnetic field. So, given this, we have our knowns being the distance between the system and the source, and we get this by using a meter stick, or in my case, a piece of tape with each centimeter marked off. We also know the net magnitude and component form of the magnetic field at a point, and this is through our software of the Tesla meter. We also found that our n is equal to negative 2.873, and that our k is equal to 6.78 times 10 to negative 7. And so essentially how we found this is, if you look to the top left, through our experiment, we were able to create the following equation of y equal to negative 2.8731x minus 14.204. And this was taken from the average distance and the average bx values that we got. And so it's also important to note that this is the ln version of the graph, which is what allows us to compare it to the equation ln of bx equal to ln of k plus n ln of r. And so through this direct comparison, we're able to find that n is equal to negative 2.8731, and that our ln of k is equal to negative 14.204. Then in order to transform this into the formula that's next to it, which is b bar equal to k r to the n, we then have to take e to our ln of k value, which then gets us the k value that I just discussed being 6.78 times 10 to the negative 7. Once we find that, we're able to plug everything into our k times r to the n formula, and then equivalent that to our b dipole formula. And essentially through this process, we were able to solve for our magnetic moment, which is also important to note that while doing this, we also approximated r to be 1 for simplicity's sake, and so our magnetic moment is 3.39 am squared. As for the general experiment, so the next part of the experiment is actually looking at the magnetic field off axis, specifically being at a 45-degree angle from the magnet. And to do this, first we had to look at a place where we had B net of 100 that was directly on the x-axis to the bar magnet. And so once we found that, we notated the distance, and we notated it as b perp, and we notated the y and the z components that we got there, which are everything that you see in the top half of the table. And this part of the experiment was run as 3 different trials, which got us the averages at the bottom. And so after that part, we moved the iPhone up by the same d perp distance, and then we redocumented what our y component was and what our z component was. And then by adding our previous y and z components, we were essentially able to correct our values, and that is what got us our b net. And our average for that is 7.653 times 10 to the negative 5. As for my code, as previously mentioned, I got my magnetic moment to be 3.39, so that is what I inputted at the top left corner of the code, and then going sequentially, I then wrote a function based off of the dipole moment formula, or based off of the magnetic dipole formula, which is also derived from the Beat's law, as previously mentioned. And so the function is essentially the implementation of the formula on the bottom left. After that, we have our B scale and distance values, and these are really things that you just had to experiment with once you saw the model in order to make sure all of the arrows are visible. And then the next following section is just me making the arrows to represent what the magnetic field looks like at different points. And so this section in particular shows our perpendicular points. And so to do this, essentially what I've done is I say r perp 1 or r perp some number is equal to whatever my observation point that I previously defined was, and b perp 1 is equal to the dipole function, the constant, which is mu mag or magnetic mu, which magnetic mu is the vector version of the constant because it's multiplied by mu hat. And then we also input the observation location that we just gotten, and then once we get a result from that, we scale it up, and that is how we get our magnetic field vectors at various observation points. And then on the right hand side, we actually are doing something very similar, but this is for the 45 degrees case. And so in order to do this, I first defined what my d perp was, which was 0.206, which I found within the experiment. And then following that, I did the same process that I did for the perpendicular and the parallel lines by defining my observation location under the r 45 degree variable, and then using that and plugging that in with magnetic mu in order to find what my b field is, and then multiplying that by b scale in order to make it visible. And then after the fact, if you take the magnitude of the vector that we received from this model, you actually find that we get something around 2 times 10 to the negative 5, which is very off from our previous received value of around 7 times 10 to the negative 5. So as for the general discussion, I would say that my results would have all been skewed by a horizontal component if we had not aligned ourselves by the Earth's magnetic field initially, as now the Earth's magnetic field is being picked up by the magnetometer. And I would say that if we had done this experiment again, and in this case, instead of having a singular bar magnet, we now had 2 connected bar magnets, I would have said that I would actually expect my magnetic field to increase, specifically like its impact on our observation location. And the reason for this is mostly because of the fact that, while both of them interact with each other, each dipole has its own magnetic field, meaning that both of them have the capability to act on the observation location regardless. Now, whether or not they cancel or not is actually determined by the fact that we're told that the bar magnets are connected, which tells us their direction effectively, meaning that both of them are pointed in the same direction. And so because of that, whatever impact we found initially will actually increase in the same regards. And normally I would say that it would almost double, and the only reason that I would not say that is because if we are close enough to like this experimentation model, the slight difference in distance between the first dipole and the second dipole to the observation location will change their impact as a magnetic field and how large they are. So that is why I say that it will increase the overall net magnetic field's impact on top of the observation location. As for general sources of error, as previously mentioned, my B net within Excel did exactly match my modeling in GlowScript, and so I would say that the major potential sources of error are the fact that there was nearby electrical equipment. Unfortunately, because I lack the capability to go in a fully electrical equipmentless environment, I was unable to avoid having some degree of impact on my results, especially considering that I had to take my computer with me so I could see the instructions within for the experiment as I was conducting it. Then on top of this, I would also say that a potential source of error is my lack of exact measurement tools. So I do not have a meter stick, and considering two were recommended for this, my method of circumventing this is taking a piece of tape and marking it by the centimeters, and then essentially using this to determine where we determine like the distances earlier in the experiment. And additionally, kind of in part with this and the lack of exact measurements, we don't know the exact location of the magnetometer, and even if we did, it's still room for potential error in my relation, in me comparing by looking at different distances and my different b net values or bx values. Because if my magnetometer wasn't exactly aligned the same way every time, then that might cause some variability in my answers, which may be another source of error for this. Thank you.